Welcome back. This is COT 3100. Today's topic is in Chapter 3 about sorting. The algorithms that we use, the popular algorithms that we use to sort. Sorting means that we take a list or a set and we take the elements and put them in a certain order. All right? That could be in a numerical order, alphabetical order, or in depending on the application in any way that we define it. So sorting is it depends. We use that sorting in a lot of databases when we gather a number of elements and we keep them in a certain database. In order to access those databases and easily and more effectively, we usually keep the elements in a certain order. And that action is called sorting. And there are a variety of sorting algorithms out there, and but we are going to look at a number of them in this section. And then some other sorting algorithms we will discuss in other chapters and sections of this chapter. The first sorting algorithms that we like to look at them is a bubble sort. Very famous, and it is one of the original ones. Bubble sort makes multiple passes, all right? Goes through the list. It wants to put the elements in certain order. Let's say in numerical order in this case, and goes through the sort number of times. So it goes through the sort to the list number of times, or we call them passes, and puts element by element in an order. So bubble sort makes multiple passes through a list. Every pair of elements that are found to be out of order are interchanged. So it keeps going to the first and the second element to see if they are in order. Let's say we want to put them in an increasing order, right? If the first element is smaller than second element, then that is fine. If it is not, it replaces them. Then compares the second and the third, and it does the same thing. Then goes to the third and fourth. Goes all the way to the end of the list. Then comes back and repeats this one all the way till it gets to the final step. And the procedure in a pseudocode format that we write, we say bubble sort. These are the elements within the list, and with n is greater than or equal to 2, meaning the list has to have at least 2 elements minimum, right? If the set or the list has only one element, there is no need to sort it because there's one element. And so then we say 1 if I is equal to 1 to n minus 1 and j 1 to n minus I, right? Then if a sub j is greater than a sub j plus 1, then interchange a sub j and aj plus 1. And what it's doing, it's going through the list, compares the first element with the second element. If this first element, let's assume that we are going to make the list in an increasing order, and it's numerical numbers. In that case, it compares the first element with the second element, and if it is first element, if it is smaller, that's fine. If it's not, it changes those two, and then compares the second element with the third, and performs the same thing. If it is second element is smaller than third element, fine. Otherwise, it interchanges those and compares the third with the fourth, and performs the same operation, then fourth with the fifth, and that would be once it gets to the end, that would be the first pass. Then comes back. Let's take a look at an example. In the example, we'll clear this option. Show the steps of bubble sort with, let's say the list is 3, 2, 4, 1, 5. All right. In the first pass, what happens? It compares the first element with the second element. In this case, the first element is greater than second element, right? In the first pass, right away it interchanges those two because the first one was bigger than that. Then compares the second element with the third one. It is okay. The 3 is smaller than 4. Goes to the third element with the fourth, interchanges those two, and then compares them, because here you notice that it interchanged that one. So 4 and 1, they replaced each other. Then then compares 4 and 5. In 4 and 5, 4 is smaller. Once it gets to the end of the list, this is end of the first pass or first section. Then goes to the second pass. Again, repeats the same operation. 2 and 3 are in the same order, so it doesn't do anything. It keeps them in the same order. Checks the second and third. It replaces those two. All right, and it goes to the third and fourth. It's the right order, and it compares then the fourth and 5. It is in the right order since 5 is the largest number, so we don't need to do that. So it goes again back here. So you see that the 1, which was at the end, almost the 1 before the last element, in each pass is being pushed 1 step higher. So finally here, 2 and 1, they replace, and everything else is in the order. But we don't know yet. Then it's going to compare, because this one, third was compared with the second, right? And it replaced everything. If it replaced 1, then we were going to go to another step. It compares the first one with the second one. Everything is passed. Now, what happens after the first step? After the first step, we know that this number is the largest. At the end of the third step, we know the last 2 are the largest. At the end of the fourth step, we know the last 3, in this case, are the largest. So then it stops. This is the bubble sort. If you want to perform this manually, it takes for a long time, but for a computer, every one of these steps maybe takes in nanoseconds, and within a few nanoseconds, you perform sorting and put the list in this right order: 1, 2, 3, 4, 5. There's another sort algorithms out there, and which is also popular, and that's called insertion sort. Insertion sort begins with the second element. It compares the second element with the first and puts it before the first if it is not larger. All right? What happened in the previous, the bubble, we start with the first element and we started comparing. Insertion, we jump to the second element and it compares that one, and then we put the third element is put into the correct position among the first 3 elements. Then we keep moving on, and this way we finish the sorting a little bit faster than the bubble sort. And here's an example. Show all the steps of insertion sort with the input 3, 2, 4, 1, 5, 1, 5, right? So what happens? It compares the second element with this one. If it is smaller than this one, replaces them. 2, 3, 4, 5. Next, it compares the third element with the second element. Third element remains in its position because 4 is bigger than 3, so stays there. And the fourth goes to the fourth element and compares him to the third one, and it is in the right place. Then goes and compares the fifth one with the first one, and it comes to be. It happens. It is in the order, so everything stays in the right place. And as you see here, it is what it is doing. We're starting kind of in the not middle, but we don't start from the beginning, and we start from the first one and comparing to the previous ones, and we are replacing it all the way. See, at this is the third element stays there, but then in the next step, 1 was compared with the 4. It was smaller. It was smaller, so he replaced that one. And then he compared him with the second one. Then he compared him with the first one. All of a sudden, changed the whole thing, right? So at each steps, at each passes, everything prior to the second one, it becomes in the right order. Here, when he compared the second one with the first one, he replaced them, right? In the next step, he compared 4 to the 3, and if it replaced them, then it compared them to the first one, to the previous one. If it didn't replace them, it stayed same. In the fourth step, 4 compared to the 3, it is okay, but the 1 was compared first to the 4, then they replaced, then 1 was compared to the 3, then it replaced, and then 1 compared to 2. So all of a sudden, 1 moved all the way to down here. This is called insertion sort. There is another algorithm which is called greedy algorithms. Greedy algorithms, as we said, in this section, we are going to look at the sorting, searching, sorting, and optimization algorithms. Greedy algorithms is one of the optimization algorithms. Optimization algorithm is that if I have a list or a set, and I want to find the maximum number in there, or I want to find the minimum number in there, and there are many applications for that if that's what I'm looking for. All right, and in that case, there are a number of ways to do it, and there are many algorithms to do it, and these algorithms are not something that are fixed. What do I mean by fixed? It means every day computer scientists are doing a research to find the best algorithm for searching, sorting, maximization, minimization, optimization, and for any one of these applications, we're always trying to improve. Improvement means to find a way to do it more effectively in less time, with minimum usage of hardware available, such as memory, right? And so among the many optimization problems we will study are finding a route between 2 cities with the smallest total mileage. This is one example, right? It is like you want to go from Daytona Beach to, let's say, Mobile, Alabama, and I want to know, is it the best, if I want to minimize the mileage, is it best to go from Daytona to, let's say, to Ocala, then go to Gainesville, or go to some other cities, and to finding the minimum route, right? Those are the typical example of the optimization problems, or determining how to encode messages using the fewest possible bits, or finding the fiber links between network nodes using the least amount of fiber, right? Anytime you need to use a resource and the resource is kind of expensive, we always then have to face with the optimization problem to find the minimum, for example, in this case, fiber, in order to make connection between a large number or some number of nodes. Optimization problems can often be solved using a greedy greedy algorithms, which we're going to look at it, which makes the best choice at each step. And making the best choice at each step does not necessarily produce an optimal solution to the overall problem, but in many instances it does. Every one of the algorithms have ups and downs, have some advantages and have some disadvantages. None of them are optimized, in other words. So every algorithm does it as best as it can, but not necessarily always comes up with the best solution. For that reason, depending on the application, we pick the algorithms that it is proven to be more effective in that certain applications. The greedy approach to solving problem is an example of an algorithmic paradigm, which is a general approach for designing an algorithm. All right, and let's take a look at the greedy algorithm. Design a greedy algorithm for making change, all right, of n cents with the following coins, quarters, this and that. What we are saying, if I have, let's say I have 75 cents, and how can I have that 75 cents with the minimum number of coins? With the minimum number of coins. If I want to have, I want to get, someone gives me $1 and I need to return them 75 cents. But what is the best solution? What is the way that I'm going to give him with the minimum number of coins? All right. And the idea is at each step, choose the coin with the largest possible value that does not exceed the amount of change left. For example, if I want to return, let's say, if I have, in this case, let's go with the example of n is equal 67 cents. The amount of money I have to return is 67 cents. All right. Clearly, in 67 cents, I should have, I pick the largest amounts of coin that I have, which in this case is quarters. So if I take a quarter off, then I compare that value of the quarter, which is 25 cents, with the remaining 42 cents. If it is less than that, what's remained, 25 is less than 42, then I take another 25 off till I get to a point that the result is less than 25 cents. 17 cents is less than. In that case, then I move to the next highest amounts of the coin that I have, which in this case is a dime, 10 cents. All right. Then I say, all right, I choose one dime. 17 minus 10 cents, 7 cents. 7 cents is less than a dime. That means now I have to move to smaller coin, smaller valued coin. Now 7 cents, the next is smaller than dime is a nickel. 7 cents is bigger than a nickel, so I take a nickel off. And 7 minus 5 is equal to 2 cents. This should be equal 2 cents. Now the 2 cents is smaller than a nickel, so I go with the smallest amount that I have, which is a cents. So choose a penny, leaving 1 cent, then choose another penny, leaving 0 cents. This is called algorithm. This is the algorithm that it minimizes the number of coins that represent certain value. For example, in this case, 67 cents. These are typical optimization problems. And here's the algorithm, greedy change making algorithm for n cents. The algorithm works with any coin denomination, C1, C2, all the way CR, depending on how many. If you remember at the beginning of the algorithm, we said the algorithm should be a generalized problem. So I'm not coming up with an algorithm which is good only, for example, in the case of a dollar, quarter, dime, and nickel, and a cent. Maybe there are some other currencies out there that have totally different types of, maybe they have a 2 cents, or maybe they have a 15 cents coin, right? So that's why we generalize the C1, C2, all the way C sub R, and then we go. So each time we take the largest one, take them off, compare the value, the remainder with the largest. If it is smaller, we take another one. If it's smaller, we take another one till we move to the next coin and the next coin, and then D sub I would becomes the coin Ci. All right. Now, proving optimality for US coins, and this is not a topic that I'm really interested, but we will look at them. We prove that this algorithm, anytime you come up with the algorithm, you also need to prove it that it is correct. And usually, beside running that algorithm and showing for certain number of coins that it comes up with the right answer, still we need to also look at them in an analytical way, in a mathematical way, and prove it. So the lemma 1 says, if n is a positive integer, meaning the total value of the money, then n cents in change using quarters, dimes, nickels, and pennies, using the fewest coins possible, has at most 2 dimes, 1 nickel, 4 pennies, and cannot have 2 dimes and a nickel. The total amount of change in dimes, nickels, and pennies must not exceed 24 cents. Why? If it exceeds 24 cents, then we replace it with a quarter, right? And proof by contradiction, it says we haven't discussed this proof methodology. So I'm going to just go through it once, so you have some idea what it is. But this is not the emphasis point of this lecture. If we had 3 dimes, we could replace them with a quarter and a nickel. If we had 2 nickels, we could replace them with 1 dime. If we had 5 pennies, we could replace them with a nickel. If we had 2 dimes and 1 nickel, we could replace them with a quarter. The allowable combinations have a maximum value of 24 cents, 2 dimes, and the 4 pennies, for instance. And here's the theorem. The greedy change-making algorithm for US coins produces change using the fewest coins possible. Proof. Again, assume there is a positive integer, and such that change can be made for n cents using quarters, dimes, nickels, and pennies with a fewer total number of coins than given by the algorithm. We are assuming that. Then we say, well, let's say that's Q prime, is a different answer, is less than or equal to Q, where Q prime is the number of quarters used in this optimal way, and Q is the number of quarters in the greedy algorithm solution. You're saying, okay, let's assume the solution, the results that produces this greedy algorithm says we have Q, or Q is the number of quarters, is Q. Let's say we say, well, it is not really optimal solutions. We should have Q prime or another number of coins. And this optimal way, and Q is the number of quarters in the greedy algorithm. But this is not possible by lemma 1, since the value of the coins other than quarters cannot be greater than 24 cents, right? Because I have the highest number is in the first pass is 25 cents. So the remainder of the money that is left cannot exceed that 24, because once it exceeds 24, then it requires a quarter. Similarly, by lemma 1, the 2 algorithms must have the same number of dimes, nickels, and quarters. So optimality depends on the denominations available. As I said, it depends on the what kind of changes we have. For US coins, optimality still holds if we add $half coins, 50 cents, and dollar coins, 100 cents. But if we allow only quarters, 25 cents, dimes, and cents, and pennies, the algorithm no longer produces the minimum number of coins. Consider the example of 31 cents. The optimal number of coins is 4. Why? Because at 31 cents, you could have a dime taken off, right? Leave 6 cents. And then a nickel, and a penny. And in this case, it should be only 3 coins. And sometimes the algorithm produces wrong answer. It gives me 4. But I can do it clearly by 3 coins, a quarter, a nickel, and a penny. So the algorithm's output in this case is wrong. We have a group of proposed talks with start and end times. Construct a gritty algorithm to schedule as many as possible in a lecture hall under the following assumptions. When a talk starts, it continues till the end. No 2 talks can occur at the same time. A talk can begin at the same time that another ends. Once we have selected some of the talks, we cannot add a talk which is incompatible with those already selected because it overlaps at least one of these previously selected talks. How should we make the best choice at each step of the algorithm? That is, which talk do we pick? So here's some assumptions. The talk that starts earliest among those compatible with already chosen talks. The talk that's shortest among those already compatible. The talk that ends earliest among those compatible with the already chosen talks. And then we come up with this also, okay, that starts at 8 a.m., ends at 9:45. Talk 2 starts at 9 a.m., ends at 10. And this one starts at 9. So can you find a counterexample here? But picking the one that ends soonest does not work. The algorithm is specified on the next page. Clearly, we can't go just by the soonest, the one that it starts, because as you see, there are overlaps which contradicts with our assumptions. At each step, choose the talks with the earliest ending time among the talks compatible with those selected. And this algorithm, we're going to discuss this algorithm later on, so I don't want to go through it, and I don't want to discuss the proof till we get to that chapter, and then we can schedule. As you see, even if you go to a conference, there are a number of people are going to make a presentation. All right, how do we optimize it in a way that in a minimum amounts of time, everybody gets a chance to talk and no talks are overlapped? All right, that's the problem. And then we have a halting problem. And again, this one is, can we develop a procedure that takes as input a computer program along with its input and determines whether the program will eventually halt with that input, meaning it doesn't fall into a loop which takes it for infinity and as a result crashes the computer. These are the kind of problems, and I'm not going to go through again to these proofs because we're using some certain contradictions, inductions, models that it's not really in the scope of this class. And I will stop at this point. In the next lecture, we will discuss the growth of f functions, which we use a big O notation, and that means how a function can grow and how fast can a function grow. What is the growth of a function dependent on? And so we were going to discuss that topic. All right, I will end this lecture at this point, and I will see you in next lecture.